Time to, well, you already took your seats. Thank you for coming to this session. We are now unmuted, so everyone on Zoom can hear you. The mics are, if you haven't been in this room yet, the mics are pretty sensitive and they're only on this side. So side conversations will be heard on Zoom if you have them on this side. Yeah. And if you're on that side and you have a question for the speakers, we will just repeat it on this side, or you can just stand up and sort of walk halfway over. And if you're sort of closer, they'll be able to hear. So, all right, this is Alert Brokers 1. This is the Alert Brokers session that's for broker users. And so for brokers to talk to broker users, you're going to see some tutorials, some talks from broker developers about how you can use the Alert Brokers. As a reminder, we have a code of conduct for this meeting. There are contacts for the code of conduct if you witness or experience any violations of that code. And then we have wear a mask if you want to. We've got some stickers for your name tags related to COVID, and then a reminder of the social battery. This is, all sessions are virtual, so we have virtual participants. I will be monitoring Zoom and the Slack for virtual questions, and I'll invite people to unmute to ask questions. We will also have virtual speakers in this session. So that's all. We get going with Eric Bellm as our first speaker. Start this. You're on the oh.
All right, it's happy now. All right.
Oh, I will give 2-minute warnings.
Okay. All right. Good morning, everyone, or wherever your time zone is. Thanks, Melissa. I was asked to give just a broad introduction to alert production for folks that may be less familiar. I know we've got a wide range of folks in the audience today. Some of this will be repeated from the early science session and other places, so bear with me. So again, alert production is one of 2 sort of major data processing campaigns that happens with the Rubin Observatory. So the telescope is going to be taking images on the mountaintop in Chile and sending them very rapidly over long-haul fiber networks right here to the US data facility here at SLAC. We're going to fire up lots of computers to rapidly process those images, calibrate them, difference them against an existing template. And for every source that is detected at a signal to noise ratio greater than 5 in that difference image, we will create an alert packet that summarizes everything we know about that specific object. And we will send it out within a couple of minutes to a handful of community alert brokers who will be the public-facing interface for this alert stream. There are also a variety of other ancillary products that get produced along the way during prompt processing, and those are also made available to Rubin data rights holders through the Rubin Science platform. Of course, just for completeness, I'll also mention we have the annual data releases. Those also do include difference imaging, and so they're a reprocessing of the whole LSST data holdings from the start of the survey to whenever that annual release is happening. I spoke of the brokers. There are 7 brokers that have been selected to receive that full alert stream directly from Rubin. They are located around the world, and many of their key people are here or online. There are ALeRCE, Ample, Antares, Bellm, Fink, Lasair, and the Pitt-Google broker. And there are, I think, at least 2, I hope there are more eventually, but at least 2 broker teams that are going to operate downstream of those full stream brokers. So I think we'll hear later in this session from David Trilling about the SNAP solar system broker. And there's also a variables broker as well. These are all teams that are working currently with the Zwicky Transient Facility alert stream, which is in many ways a lower volume prototype of the The alert distribution is technically based on a couple of open source components that come to us from the commercial internet industry. There is the Avro data serialization format, which is a binary serialization, strongly schemaed. It's relatively compact. It is challenging to get data into because you have to get all the data types right. But once you've done that, the downstream user will always get the right thing with very little parsing. And then Apache Kafka is the system we use for alert distribution. It is a real-time distributed messaging log that allows our broker partners to listen, catch up, replay the stream fairly efficiently. All right, no worries. All right, I mentioned briefly, but let me summarize in more detail the data products that are produced in alert production. The first is, of course, the alerts. Those are the real-time data product. They are triggered, again, by that signal-to-noise 5 or greater detection on the difference image. And again, we make an alert for every object that meets that criteria. Whether or not it was seen for the first time in this image or whether we have 10 years of history, we always send it out. That allows the downstream user to conduct the most flexible science, whether discovering new supernovae or looking for unusual variability from variable stars. You could have an RLI that is sinusoidal, like smoothly varying for 10 years and all of a sudden does something strange. If that's something you're interested in, you can construct a filter with a broker for it. So in addition to that triggering source record on the difference image, there's also an object record that has time series statistics and some other summary measurements. There are postage stamps of the difference template and science images, as well as a light curve, a history of those past detections that you can use to look for variability. The catalogs that go into the alerts, everything that is packaged up, is also available for query in something called the Prompt Products Database. It's a relational database. It will be exposed for Rubin data rights holders through the Rubin Science platform behind a tab service, if that means anything to you. That's within 24 hours, maybe a little faster, depending on how soon we can replicate it. Yes, Osley, question.
For the DIA source, if this is a brand new source, will the entire database be populated before, with all of the columns be populated before, within the 60 seconds and before the alert is sent out, so you get the full source record even for a brand new source?
We do make the DIA source record itself is just a measurement on that image, so that's produced automatically. We will make a new DIA object record that summarizes what we know about it, which is not very much. You'll see, okay, this is the first detection. There will be some upper limits, so you get an idea of when it was not detected last. But there's not going to be detailed time series features for something we have one data point of, for instance. And finally, the images themselves processed through prompt processing become available again through the RSP after 80 hours. So if you wanted to trigger your own custom pipelines or do detailed analysis, that's the timescale that's relevant. If you want to know more about what those catalogs contain, I'll point you to a document and a website. The document is the data products definition document, which has sort of been our long-standing guide to what we're trying to build. It sort of summarizes in fairly lengthy detail the processing steps that are planned. It is under fairly strict project change control, which is great, but it also makes it a little hard to update. And so it is not always as current as we'd like it to be. So I also want to point you to the Science Data Models schema browser, which you can get to with ls.st/schema. And there are a number of different schemas that are relevant. You see the data previews, 0.3, 2, and 1. For AP in particular, the alert production database schema is the relevant one. And you can click through there and see live, what the column names and types and so on and descriptions are that we're processing right now. You saw this in our early science. Again, we're expecting to begin sending alerts near the start of the LSST main survey at the end of commissioning. They may not be at 60-second, that they will not, we are unlikely to be at 60-second latency at that point, and we have to ramp up slowly with coverage. So that would be kind of a slow turn on as we build up templates across the sky. But throughout the first LSST year, we'll get more and more alerts and build up capacity that way. We're working with the broker partners that you'll hear from later today to make sure that we're ready for this first alert release. We're sending alerts that are from processed simulated images, including during the last operations rehearsal. We replayed those images from the summit, sent them over the networks here to the USDF, and sent them out to a subset of the brokers who chose to connect. All of this alert data we're treating as world public, and so we're going to focus on simulated data until we're ready to send the real alerts. There will be a milestone that the first release of public LSST-CAM alerts. There's a document here, which I'm going to RTN 61, that talks about what we have to get ready for that. In particular, we need a formal approval from the agencies to start that. And so as a result, we will not be sending any alerts from ComCam. First alerts will be from LSST-CAM. And again, if you're interested in how all this fits in sort of early science, along with the other data previews from commissioning, the relevant reference is RTN 11. And you can always ask questions at community.lsst.org. All right, I will pause there and take any questions. Yes, Igor.
Have plans for force photometry to be included in the alerts been finalized?
We do intend to provide force photometry in the alerts. Obviously, it will be previous visits with force photometry. But yes, we do intend to provide force photometry in the alert packets.
Sorry for the follow-up. Just do you know like how many epochs, and also how do you set your centroid?
Centroid will be from the DIA object centroid, and I think we're still understanding some of the database performance, but notionally we like to try to provide everything that is available. And so when there's a new detection, we go back 30 days and get force photometry on those. And for objects that are sort of regularly being detected, we will follow those along. And so you could, in principle, have a year of force photometry. And whether we can actually get the databases to turn that around fast enough, we still need to understand. But we aspire to provide force photometry when we have it. Thank you.
Yes. In the past, people have been talking about in the crowded fields, there might be problems like processing it fast enough.
Yes.
Is there any updates on how that will be incorporated into alerts?
That's a great question. We are required to do alert production in fields of all crowding levels. It is more challenging. There are a lot more sources. It's a lot denser. With that said, difference imaging was invented to process crowded fields. So I don't have any concrete updates in terms of timing. That is something we are working on. We have a crowded field data set that we are using as a test bed from DECAM. And we're going to be getting back to that in the next month or two to try to make sure that we're ready.
Following on Igor's question of the force photometry, and
yep.
For the case of the deep drilling fields, in the last tick challenge, we noticed that was a lot of redundant information that was sent one and again and again and again.
Yep.
That was very heavy and dominated actually the alert stream. Are there any plans to alleviate that problem, or?
I think that's a conversation we should have with you, the brokers, in terms of what's useful. Absolutely, you're right that the DDFs in particular and force photometry tend to dominate. And there's no point in us working hard to send you information you don't want. And so I think we should have that conversation with all the brokers and make sure that we're giving you the most useful thing.
Yes. Can you expand on why you decided not to release alerts for ChemCom?
Yeah,
it would have been useful for from the perspective of the brokers to process some of your data.
Yeah, two reasons we are not releasing alerts from ComCam. One is, if you look at the observing plan that Keith Bechtel was presenting, it's not even clear that there's going to be very much data that we could even difference, depending on it. It's a very compressed schedule, and we're not certain that that's actually possible. The other is, again, that we've been asked by the agencies to go through a formal review, and that is scheduled after ComCam. And so we're simply not allowed to release alerts until we've been given permission. Yeah.
So verifying, my understanding that the first alerts from ALeRCE and then yesterday in one of the sessions, they talked about ALeRCE CAM data coming out in 2026. So is that like different? Like the alerts come out in 2025, but it's not like the data is not available until like a year later, or what's that like? I guess difference.
Yeah, great question. The question was there was a little confusion on the messaging probably in the early science session about ALeRCE CAM data being available in 2026 in DP2. The difference is DP2 is a data release that is sort of uniformly processed that takes a little more time, whereas alert production is sort of done on the fly, and so we can start that a little faster. I'm going to have us update those charts to make a little clearer how alert production fits into that scheme, because it's easy to sort of forget that, but it will come first. Is there a
no?
Gautam has a question.
Oh, hand is up. Okay, go ahead, Gautam.
Hey, Eric, just following up on Francisco's question about the DDFs. A lot of the reason the DDF alert volume is so large is just because of the number of exposures on the DDF every single night. And one way of reducing that, of course, is to co-add exposures within the DDF during a single night. I was wondering if there was more progress on whether alerts could come from nightly co-ads and what the status of all of that was.
Yeah, so as you know, there has been some work by Bob Armstrong and some of your colleagues in desk to prototype a co-ad pipeline for the DDFs. I think that it is certainly plausible to think about making that an official product and releasing alerts from it, but I don't have any update in terms of timeline there, and I don't think that would run in real time in any case. It would probably be an end of night sort of production just for a variety of reasons. So yeah, no immediate updates there.
Thank you, Eric. Thanks everyone for the questions. Let's thank Eric again. Right. Next is Roy. Next is our Lasair talk. It's either going to be Roy.
Yep. Do you hear me?
Yes, we do hear you. We've let you should screen share.
Okay, let me let's see. Do we have that now?
Yep.
Oh, come on. Okay, do you see the large Union Jack at the bottom there?
Yes, now we see your slides.
Good. Lasair is an Edinburgh, Belfast, Oxford production. And I will say that I'll be talking about fixed objects in the sky, but we do have a subsidiary project called ALeRCE, which is dealing with solar system objects, which I shall not be mentioning, but that will be coming later. So Lasair is sort of a way of users to create their own filters. It's not classification of alerts, but rather building a filter that reduces the deluge down to just the ones that you want. And there's various Lego bricks in the box, watch lists, watch maps, light curve features, the Sherlock context system, annotations from other people, and we have a sharing system of all of these resources if people wish to. So you can take a filter that someone else has built and modify it for your own uses. A watch list, I think we've all seen this before. It's a set of points in the sky, each with a radius, and whenever an alert comes near to one of those, then you can put that into your filter, and you can have a million or so in your own watch list if you wish. Lasair filters are built from geometric and tabular information. The geometric information, for example, this watch list idea or the related watch map idea or the sky context, but the tabular information is put together with SQL filters from a number of tables. And you build a selector a clause in SQL and a where clause, a constraint clause in SQL, and you can add in these various watch lists and watch maps and annotators to make a very rich filter. The object page carries lots of information. There's, let's see, top left, basic information with a go deeper so you can find more. There's the TNS if the object is in the TNS, the Sherlock Sky context system, the light curves, top right is Aladdin Light and the various cutout images. Again, all of this has buttons labeled go deeper, which tell you more and more about the object. And all of this stuff that you see on the web page is also available through the Lasair API. So our key concept is this idea of active, that you build a filter and it selects out just what you want from all of the alerts. And by the time you've fiddled about with it for a while, you turn it on and make it active. And you see down in here where it says streaming, you get a choice of email or Kafka. Kafka is sort of the modern way of doing things. It means that as soon as an alert comes through that satisfies your filter, that is allowed through by your filter, it immediately goes out on a new Kafka stream, and your machine or your marshal or whatever can take that. At bottom left here you see you can click to say public if you want to share. Sherlock is a whole collection of catalogs, and I won't say what they all are on the left, and on the right are the classifications. So variable star, cataclysmic variable, bright star, AGN, nuclear transient, and supernova. They don't mean that it's an actual nuclear transient or supernova. It means that it's associated with a galaxy, and if it's nuclear, it's near the middle, and if it's classified SN, it means it's in the outskirts. And so you get an English language description up at the top of what Sherlock thinks the association is. Light curve features, Eric has produced a document with lots and lots of periodic and stochastic features, and we've tried to add some features for immediate rapid transients. For example, flux jump is about signal to noise of the latest flux above the previous levels. It's a very simple thing. We have this Bayesian black body thing on the right, which does a two-dimensional fit of Bayesian in time and black body in wavelength. Fast Finder is another set of features that we have that look for rapid incline and decline. So the annotation idea is that you build a filter such as written here and described earlier, which produces its own Kafka stream. And now on the right is your stuff, where you receive this Kafka stream and do some computing on the information about that object, and then make a decision as to whether it's interesting or not. And if it is interesting, then you can send that back in again as an annotation to Lasair so that it records what you've done, and it also allows other people to see the results of your annotation. Let's see, we have permission from ALeRCE and Fink to suck on their Kafka streams, and we are integrating those into Lasair so that you can make queries through Lasair about what Fink thinks this object is. Recently we've been doing work on gravitational wave sky maps, and what you see here is the red mock is the 90% of the probability is inside it. The yellow one 50%, and the cyan one is 10% of the sky map. And there's some there's some white and green circles there, which correspond to counterparts, possible counterparts that look interesting. The bigger the circle, the more likely it is to be the counterpart. There's two kinds of counterpart. There's the 2D ones where all we know is their position on the sky, and we know the probability density from the sky map. The 3D kind is a bit more interesting because we have a host galaxy with a distance, and therefore we can use the distance probability density that is also supplied with the sky map. So those are much richer in a way. So here we are. Lasair has a movie, and I encourage you to search for Lasair the movie, and it's got my favorite Edinburgh pub in it, and various other bits and bobs. And what Lasair does is allow users to build filters using watch lists, watch maps, annotations, features, all of this stuff can be put together using SQL and so on to build this filter. Lasair has added value, this intelligent cross-match of Sherlock, the light curve features, the annotations, the multi-messenger stuff. And it's a real-time system in the sense that the data comes in, is processed, is filtered, it goes out on Kafka, it gets annotated, and a follow-up can happen, and all of this can go on while the humans are sleeping. And I feel like it's time to stop thinking about this old web model that we have of requests and responses and start thinking about an ecosystem of Kafka streams so that these filters, so that streams of alerts come in and get filtered or value added to them and then go out again. And, we can connect up networks of Kafka streams in an ecosystem. That's my big idea today. So thank you so much. Are there any questions?
We have time for a few questions. Yeah, if you want to just come a little closer to the mic.
Hi, Roy. Can you hear me?
Yes.
When you have annotations and send them back, what information goes into those? Is it your filter? Is it your results? Is it just notes that you take?
The annotation has certain fixed fields like who produced it and what object ID it came from and so on. But it also has a schema-free JSON packet that goes along with it. So that's whatever the builder of the annotator wants to put in there. And those JSON fields are queryable as part of the filter system.
Right, thank you. Any other questions for Roy? Yeah, if you want to also come a little closer. Oh, just there is good. That's the mic right there. Yeah, so you're good there.
So could you expand a little bit on the multi-messenger, I guess, features or capabilities of Lasair? I don't know if I pronounced it right.
Well, it handles these. We're used to the idea of sources in the sky being a position and a radius, but with a gravitational wave, you get this sky map of complex shape. And so you can look at all of the alerts that come through, the optical alerts, and try to match those to the sky map and ask which of them have the highest probability. But then you can go further and ask which of those alerts have a distance through a host galaxy, so that you can then utilize the 3D part of the sky map as well as the 2D part.
The mechanics as well is that we're listening to the Kafka stream from the GCN. So as soon as anything appears on the GCN, we immediately ingest that into Lasair.
Thank you.
Final questions for Roy? right, let's give her another round of applause. Next up, we'll have Christopher Hernández. Yeah, we're going to be talking about the Pitt-Google Alert Broker. You should be able to share your screen if you're in the Zoom. You can share it in the Zoom.
So hello, everyone. My name is Christopher Hernández. I'm a PhD candidate at the University of Pittsburgh, and today I'm excited to introduce you to the Pitt-Google Alert Broker. The Pitt-Google Broker is an alert distribution service that adopts cloud-native technologies and methods that are unique in the space to enable broad public access to and scientific analysis of astronomical alert streams with low barriers to entry. We achieve this by using the following Google Cloud services to serve astronomical data, and this includes Google Cloud PubSub, BigQuery, and Google Cloud Storage. PubSub is an asynchronous and scalable messaging service used for streaming analytics and data integration pipelines to load and distribute data. We use this as our intermodule communication system, and users can leverage PubSub to subscribe to the variety of message streaming topics that we have. And these fall within the 3 categories that you see here. So this is an outline of what we currently have in production for ZTF, and you can expect to see something similar for LSST as well. So we will be streaming the full alert stream. So in this case, we are streaming the full ZTF alert stream and its derivatives. We have a set of notification streams and a testing stream that's used internally by developers. For long-term tabular data storage, we use BigQuery. And again, you can see the different categories that we have available. Mainly alert data and information and classification results as well. I'm also excited to announce that we have recently updated our broker to listen to the LIGO Virgo Cogra alert stream. And so again, as well, we are publishing the full alert stream and loading that data into BigQuery. And now I'd like to turn you over to the Pitt-Google client. You can scan this QR code to follow along or store it to review a little bit later. But the Pitt-Google client is a Python library that contains the tools to interact with the Pitt-Google Broker data resources on the Google Cloud platform. On this page, you'll also see a section titled One-Time Setup. You can follow those instructions to basically set up a Google Cloud project to interact with the services that we provide. You'll see a more detailed instructions on how to authenticate to that project and set some environment variables. I'd be happy to walk you through that, but due to the limited time, I'll just continue moving forward and demonstrate a live tutorial of how to use the services that we provide. Is this big enough, or would people like me to zoom in? Okay, great. So as I mentioned, users can leverage Google Cloud PubSub to subscribe to the variety of topics that we have. So in this notebook, I've authenticated to a Google Cloud project and imported the necessary libraries. Using the Pitt-Google client, I can specify the topic that I'd like to subscribe to by passing in the name of that topic and the project that it resides in. I'll define a subscription that I'd like to create to that topic. I'll name it, specify the topic, and provide the name of the schema and create it using the touch method. Using the pull batch method, I can pull an alert from that subscription and convert that into a pandas data frame. And using this function that was provided in the public notebook in the CTF GitHub repo, we've adapted this function in order to plot a light curve. And so I'll pass in the pandas data frame, and we can take a look at one of the alerts that was in the subscription that we created. If you'd like to take a deeper look into this object, you can also use BigQuery to query additional information. So again, I have listed some additional commands that you can use to get more information about what we offer. This is a list of tables that we have within our data set specifically for ZTF. Again, I'll specify the table that I'd like to query from, and you can take a look at the schema as well. Using the object ID that was found in the alert from the subscription that we pulled from, I'll write up a SQL query and submit that query using the Pitt-Google client. And as you can see, that returns the results of our query. I'm also happy to announce that we are in the process of implementing a tab service as well. So you will be able to access the data within our BigQuery tables using tab and ADQL. And one of the things I haven't mentioned yet is the fact that you, if you are interested in, and depending on your science case, can implement your own classifier and use the data services that we provide to run your classifier. We recommend using Google Cloud Run. It's a service that runs containers, and you can use a PubSub subscription to trigger your classifier. Again, there's a lot of details behind this, but kind of the main idea is that you need the following files to containerize your classifier. You're going to need the source code, a setup script to deploy the module, a Docker file, and a YAML file that contains the instructions used by Cloud Build to build the container and deploy that to Cloud Run. And so to summarize, the Pitt-Google Broker serves astronomical data through Google Cloud Services. This is unique in the space. We use scalable cloud-native services that are managed by Google and are accessible to the public through APIs. Again, the most commonly used services are PubSub, BigQuery, and Cloud Storage. And for further documentation, I'll refer you to the Google client. If you'd like to connect with me on LinkedIn and continue a conversation virtually or in person, please feel free to do so. Thank you.
Questions for Christopher?
Just a question. So you said you're doing a tap client on BigQuery, and have you spoken to Ross Thompson from Google? Okay, just to,
Chris, could you maybe comment on, I love this, is really a great example. As a user, how do you sort of develop some intuition for the cost involved with the various steps here? Because that's obviously the challenge in a cloud environment.
Yeah, that's a really good question. I think it depends on what your science case is. We've had conversations internally about, additional things that we are going to implement into our broker that may be of use for users. We are also working on developing some pricing models to give users a better idea of what they can expect.
If I might, one of the things, if we do a tap service, for example, it actually answers that question too. Because we'll just pay for running the tap service.
Sure.
And, so there are a couple of things like that we might do. We spend a little under $1,000 a month to run and store all of ZTF for however many years. So we certainly don't anticipate any actual users should have to spend anywhere more than 10% of that. but we also recognize that sometimes it's obnoxious to spend $100. But in terms of cost model, that's where we feel like it is.
I think most useful would be like, okay, if I wanted to subscribe to ZTF Lite and receive everything, how much does that cost? If I want to run my own Cloud Run on the ZTF alerts, which are larger, like what does that look like? You know, I think a couple of touch points there might give folks an idea of like where they can plug in easily and cheaply, or you know, where you're talking about like, okay, that's kind of a big lift.
Yeah, no, the Cloud Run's an excellent example. We have that, and let's finish that paper.
All right, let's thank Christopher again. Hey, okay.
Okay, so hi everyone. I'm Alejandra Muñoz-Arancibia. I'm a postdoc in Chile working in ALeRCE, and I'm happy to talk to you today about what we can offer to you to do science. These are the people that are currently part of the group, supported by institutions in Chile and abroad. Just in case you don't know, ALeRCE is a Chilean-led community broker, and we are led by Guillermo Cabequera Vives. He's our PI, one of the founding members, and also we have members from ALeRCE here today, Francisco and Marcio. And online we have Franz and Ignacio Reyes Gainaga, who is our lead engineer. So the main idea driving this presentation today is that you can already do science with ALeRCE, because for many years we have been striving to be the intermediary between the large surveys and the community and follow-up facilities. And for that, the public stream from the City Transit Facility, CTA, has been essential. We have learned a lot from that. We have ingested this stream for 5 years and providing to the users in real time, publicly, visualizations, classifications, machine learning classifications, and also access to the data through several means, but in particular a Python client, an API, and a database connector. It is a SQL database. And also something that is essential for us in all this preparation, this road to Ruby, is that we want this arrow here to be both sides. We want to hear from the community. We've been hearing the community, especially if you are just starting with brokers or have been an active user of brokers and of ALeRCE in particular. We want to hear from your feedback, the things that worked for you, and especially the things that haven't worked yet for you. For instance, if you have science cases that we have still not included, we aim to be flexible for that, especially preparing to the Ruby net. What we offer to you now from CTF, and I will present this mostly regarding CTF because you can expect that most of the services, even taking into account the differences between the CTF stream and what will be the LSST stream, we expect most of our services will be very similar to what we provide now, and also want to keep improving. The main product in terms of machine learning classifications are the stamp classifier and the Likert classifier. The stamp uses the first three read of the stamps, and the Likert includes several science cases, several classes, including transient, supermassive black holes, and variable stars. And also note that the Likert classifiers involve computing in real time several Likert features. We also provide them to you through our database, and we also recently released just like a piece of this database of features to you. So you can point to them in Zenodo and explore the data yourself. The main way to access this data are the web interfaces. In particular, the Explorer is quite powerful. You can explore the live curve, the stamps, and ancillary data, and also the classifications. And recently, we added some features to this Explorer. In particular, we also can display the light curves in flux besides magnitude. And also note that since the last year, we are also including the force photometry. And it's essential, for instance, if you just include the detections, you cannot track, for instance, for transients, the early part of the light curve. So it's very useful to have this information, and that is available for you. Also, if you care about variable stars, we also added an option regarding the periods. You can play with this in a more interactive fashion. We already provided as a feature the period of the light curve. You can fold the light curve, but if you're, for instance, not happy with what we provide, you can explore and provide your own period, and even play with a periodogram and do this in a more interactive fashion. So that is one of the main tools. And another big one is the Supernova Hunter that we use to search for early transient candidates. And also we provide a watchlist service. And you can learn how to use all these tools via the documentation we provide in our GitHub repository, in our website, and also in our YouTube channel. We have information about the workshops that we can, videos about the workshops that we have. As an additional service, we also report early transient candidates to the transient servers, which is the official means for that of the IAU. We report transient candidates from the CTF stream shortly after the first detection, and that it enables and is enabling the prompt follow-up. We report a lot to these years, but it's not only the number that counts, it's also the purity of the sample. We have a very high purity, for example, in terms of the spectroscopically classified supernova, for instance, and also a large fraction of tidal disruption events reported to the transient server. And already people are doing science with ALeRCE. Many articles, close to 200 articles, are mentioning ALeRCE. Some of them are ours, from our collaboration, and spanning several science cases from transients, supermassive black holes, and variable stars, and also some of them focused in the infrastructure part and the machine learning. And also there is a lot of science by uses through the years. And here I just include some examples. This is a non-exhaustive list of the works that use ALeRCE, just for you to get inspired about them. I will go quickly through them, but I include the links to these works just in case you want to look into more detail today. The most basic is exploring the CTF data to our ALeRCE Explorer, for instance, this was just mentioned, for this candidate tidal disruption event, and include the link to our Explorer. And also a big use of our services is downloading the CTF data. Here, spanning several science cases from supernova, rapid transients, TDEs, active galactic nuclei, and also some variable stars. Also, some people are including our information when they report transient candidates to the DNS, only including us, or together with the other brokers that are ingesting CTF. We fully support that. And also some people are cross-match, using the data that we provide to cross-match with other surveys. For instance, this is a blind survey where they were able to a posteriori classify supernova based on the spectrum given by this survey. And also a very big use that we have noticed is selecting targets for the follow-up of studies on the classifications that we provide. This has been very strong, for instance, in transients, also in AGNs and cataclysmic variables, and even for citizen science. Also, there are works that use the ALeRCE classifiers as a means to pre-process another tool. For instance, this work that is focused on transients and in anomaly detection. So to separate between the transients and those that are not transient, they are using ALeRCE. And finally, this is another work that also was presented yesterday in the conference that uses the code that we use for computing features. You can use it on your own. It's available in Zenodo and also has a link to the GitHub repository. So I just go back to this slide, highlighting the main tools and also how you can go to them. And something a little, how it looks the near future for us, we are aiming to include new light curve classifiers based on CTF data that will include even more light curve features, also use the force photometry points that we recently started to ingest, and also include new classes. And this is one of the cases where we hear the community caring about fatal disruption events and microrensin events. We are including them now in this classifier that will be released soon. And also searching for anomalies in real time is something that we are also striving to include. So stay tuned for that. And again, I want to express the idea, just let us know and give us your feedback. How can we help you even more to do your science? Thank you.
Any questions for Alejandra? Yeah.
So for the ALeRCE broker, is there any plan to have like filters like Lasair so that user can filter out like what is interesting to them?
Yes, actually, I didn't mention in the watchlist service, we're also currently working in improving that, including filters. That is work in progress, and we hope to also release.
Yeah, and Evan, you want to come closer to the...
You mentioned there's a Nodo paper with a database of all the alerts. Can you a little bit talk about that and maybe what's the plan for the future when this will start to be, expanding, and how sustainable it is?
Yes, this idea mainly started because we wanted to start with these new features that we are hoping to put into production soon. So we wanted to freeze the database so that to compare, and also aiming for reproducibility of the features before and after, because we don't save all the features. We update it every time there is a new detection. So this was at May. Hopefully when we start in production with the new one, we will release another one. And in terms of how regularly we will provide this, I think that is not settled. But if there is a necessity from the community, we'll be happy to discuss that. How would that work?
A final question for Alejandra? All right.
Hello, I'm David Trilling. I'm going to talk today about the Solar System Notification Alert Processing System, SNAPS. I don't think this audience needs a lot of reminders here. ZTF, as Eric said earlier, is sort of a pre-LSST. LSST, as Eric also said earlier, we're going to have some alerts coming 2025, so next year at some point. And so I'm going to talk about SNAPS here, Solar System Notification Alert Processing System. This is a downstream LSST broker, and Eric mentioned that again at the beginning, and I'll just tell you a little bit what I mean by that. I'm not going to spend a lot of time on our architecture here, but I do want to point out over here on the right side, our database, of course, is the core of our broker. We could either be listening directly to a ZTF or an Atlas or an LSST or anybody else's stream, but in fact, what we're doing is listening to a substream that's rebroadcast from Antares. So that's what downstream broker means, is we're not listening to everything that's coming, but only the solar system objects that are coming from Antares. So Antares listens to the whole stream from ZTF or future LSST and rebroadcast solar system objects, and that's what we're listening to. Okay, the architecture is presented in this paper from last year. We have a whole lot of other papers here. Let me just talk about these two channels in our architecture here. We have in the red on this right side is what we call real-time outliers. So this is a solar system object whose properties have changed from one observation to the next. And I'll show you an example of that in just a moment. And those are the transient universe, so to speak. That's on this sort of red channel here. And the blue channel here is what we're calling our daytime outliers, or population outliers. They have properties that are consistent from observation to observation, but they are unusual compared to the rest of their population. And those require different kinds of processing and different sort of alerts and handling. So back to this paper list, you can see that we focused mostly so far on our population outliers, and we're now building up our individual outliers component, and I'll talk about that. towards the end. Okay, and I just want to highlight that there's a solar system science session this afternoon. Maria Chernyavskaya will present on her work, and Mike Gowanlock on his work, both of which are population outliers. Okay, so this is important to briefly discuss what SNAPS does and what SNAPS does not. Okay, so on the left, what SNAPS does, we're ingesting observations of known asteroids. We're deriving various properties of those asteroids. We have a value-added catalog, and we're identifying outliers of different kinds, as I mentioned. What are we not doing? We are not discovering new solar system objects. We're not, at the moment, handling comets, although we'll get to that, and I'm not interested. We're not doing anything with non-solar system objects. So it's a pretty, maybe it's fairly obvious, but I think it's good to write those things down so that it's understood what we can and cannot do. At the moment, we have something like 10 million asteroid observations in our database. We're deriving properties for any asteroid with more than 50 observations. And so we have about 100,000 unique asteroids right now, which is about 10% of all known asteroids. That's pretty cool. LSST is going to, of course, be something like 10 times that in the first few years and maybe 50 times towards the end. Okay, so let me show you a couple examples here. This is our, I think I had this in the red channel. Anyway, this is the real-time or individual outliers. And I realized that I have busted my presentation by turning it into a PDF. So we'll see what this actually looks like. Okay, so we have, this of course is ETF data with the RNG filter. On the left side, I have time and then brightness on the y-axis. And over here on the right side, this is heliocentric distance and brightness. And so, on the left side, you can see this cyan arrow showing you where time is, of course. And then time has this funny pattern on the right side because the object is in closer to the sun and then starts to recede. And what we see is that, maybe you can see this most easily on the right side, as you're getting close to the sun, I guess it doesn't matter if I wander around, as you get close to the sun, we have this sort of flat, brightness, absolute magnitude, and then the object gets brighter. Here's perihelion, and then the object fades as soon as you get past perihelion. And so this is a classic signature of what an active asteroid would look like. And this is the slide that's busted because I don't have my animation here. But here's Julian date on the x-axis and heliocentric distance on the right. And if I had gotten the animation right, you would have seen at these different spots that the PSF goes from very tight to very broad, and clear sign of activity right here at perihelion. So this is an asteroid that grew a tail or a coma or something as it got close to the sun, and then that fades as soon as the asteroid recedes from the sun. That's great. It's a pretty interesting physical phenomenon. This is not the first one. There's known to happen for other asteroids, but a uniform survey such as ETF and then LST is going to be an incredibly rich database of these kinds of objects. Okay, here's another one that popped out just sort of by happenstance. Again, this is time and brightness and the G and R filter from ETF. And it sure looks to us like this is an object that the G minus R color is basically 0 here, and then it actually gets quite large, and then it is starting to converge again. And so that is a signature of an asteroid that maybe is changing color. That's a little bit unusual. There's not very many data points here, so you might squint your eyes and say, I don't believe it, but that's okay. The point here is just to say that we have many examples that we're finding anecdotally. You tell me your favorite asteroid, we go look it up. Oh, that's weird, and oh, this one's weird. And so there's an awful lot of unusual activities that this kind of database is revealing that has not been seen before. And so underway, we have sort of half built some of the algorithm detection schemes that we're going to employ for some of these cases. I'm going to briefly also here tell you about our population outliers. This is what we call daytime processing. So, during the day after all of our nighttime alerts have been ingested, we can then look and say, okay, which of the asteroids in our population look unusual compared to others? At the moment, we're working at the 15-dimensional feature vector. These are properties of the asteroids. There are several flavors of this outlier detection, and I refer you to Mike Gowanlock's paper, which I think was published last week. So there's a lot of details there. I'm not intending that you should understand the axes on this plot. In fact, I'm not even going to tell you what the axes are, just to say that these are 4 instances of the same three-dimensional slice through our 15-dimensional feature vector. And the four figures here are showing you, excuse me, 4 different outlier detection schemes. And this is a little bit of a test to say, okay, well, which schemes are going to be the most effective? In fact, not the lower right, but the other 3 seem to find the same set of outliers, the red points, compared to inliers, which are the blue points. This scheme over here, which I can't actually remember which one this is, finds a completely different set of or almost different set of population outliers. So we're trying to understand how best to approach this outlier inlier detection across our feature space. Okay, so here's my last slide. Just as a reminder, or no, I've said some of these things, but as an update, this is our next steps. We're working on this algorithmic real-time detection. Our public-facing web page it exists, but it's a bit crude, so it needs a makeover. And our outgoing alert stream for real-time and population outliers is underway. We're doing our daytime and nighttime processing, but not in a production mode kind of style, so that's coming. And we think we're going to be ready to operate at LSST scale. We think we've surpassed some of the major computational hurdles, and we'll do some more testing on that over the next year. Finally, I just want to advertise again, Maria's talk she's going to talk about asteroid strengths, but in the context of our ZTF work and looking ahead to LSST. And Mike, these are both remote talks. Mike's going to talk about some more about that population outlier work. I unfortunately have to run away right after this session, but I encourage you to ask Maria and Mike all the hard questions.
I want to start with a question from Slack. If you could define a little bit what you meant by asteroid, like only things with minor belt asteroid orbits, only distances less than 5 AU.
Yeah, let me go back to this does and does not do. I think this is probably what triggered that question. Yeah. We are considering any solar system object that's not a comet. Okay, and if you want to know what is a comet and what is a not comet, it's both a technical question and a philosophical question. But back to the details of the Slack question, anything in the solar system that has a designation and orbit from the minor planet center and so on is in our database. And we can do more follow-up on Slack after that. That's not satisfactory.
Any questions in the room for David? Go ahead.
Whether or not an object's extended, pretty relevant to this question, but some are like just a little bit. It might depend exactly what the PSF was in that image versus another image. Does that get reported through MPC, or is that something you're going to go and get from Rubin? Like the extendedness was no greater than this because we have a good image, but it was 1 arcsecond scene, versus this other time we got 0.6 arcsecond scene.
Yeah, so the metrics for those are coming in the metadata with the alerts, where you have an elongation measurement, you have a real bogus, you have various other things. And so we don't use a single parameter. You wouldn't say, okay, well, the PSF was this, and all the other history was that, therefore it's active. So we have this multi-dimensional thing that if you have a fat PSF, skinny elongation, you would look through that space and say, are you inconsistent with the history of this object in that multi-dimension? There's not a single, we're not using a single parameter, but it's not coming from MPC, it's coming from each of the alert packets.
Yeah.
I have just one more question from Slack. Yeah. So the web interface, Kafka interface currently being developed, is Snaps going to be ready with a URL and web interface for the science validation service? I guess when alerts start? Or...
Sure.
Okay. Let's thank David again. Next up is Anais, and she will be sharing. Anais, you want to unmute, make sure we can hear you?
Yes, hopefully you can hear me now.
We can hear you, yep. And
perfect. And you should be able to see my full screen now.
yep, and we can see your slides. Perfect.
Perfect. Okay, hello everybody. My name is Anais Möller, and I'm going to tell you about Fink Broker. It's a very wide collaboration. You can see some pictures of some of our members here. So this is a community-led effort. The three PIs is myself, that I live in Australia, Julien Peloton and Emilie Ishida, who lived in France. So it's a very atypical broker in that sense. We're three PIs around the world. So today I'm going to tell you a little bit about Fink in general and a tutorial of our services. To give you an idea, what we're doing right now is we're deploying with CTF in a virtual data cluster in the south of Paris. We're getting around 200K alerts per night from CTF, and we're having around 100 unique daily users. And we have a data transfer service that I'll show you with more than 100 million alerts downloaded per month, which is huge. For Rubin deployment, we will be deployed in the supercomputing center in France in IN2B3, in CC IN2B3 in Lyon. And we will have a much more bigger resources, but we have stress test everything and we are ready for Rubin volumes. Everything is open source in GitHub, so you can look very clearly what we're doing, our software, and of course, the data is public. Now, I cannot tell you in 7 minutes all the science that we're doing, but this is a community-driven effort. So as more community and more people join, we can have more topics, and we really want to have as many science topics as we can. We have a lot of people working with supernova, from traditional type 1a to pair instability, nuclear transients, solar system objects. We have a partnership with Euclid. Kilonova, we have partnerships with the Gamma collaboration. Gamma Ray works with SVOM, which is a space mission recently launched. And we're working also preparing with simulations with LSST. But I'll tell you a little bit of how to access more services than the science that we're doing. If you're interested, drop me a line. We can tell you much more about it. Now, in a nutshell, what Fink does, it ingests all the alerts. It does cross-matching with catalogs like Sinbad, Mangrove, but also survey streams like GCNs, especially for gravitational waves, neutrinos, VOM. And then we have a lot of machine learning features as well, like random forest classifier, supernova, which it was mentioned today in the session. That was a classifier that I created. And we have several modules depending on the target. We have anomaly searches, and we're working with active learning as well to improve these classifiers. Once you have all that information, you can filter. That's completely customizable. And we can have two ways of accessing the data. One is through our database, REST API, that I'll show you how to get it through the science portal, or also like automatically to schedule follow-up or having a live stream. In the idea of having a live stream, aside from reporting TNS early type 1a supernova candidates, we're also working to integrate with telescopes. So we have a system created to automatically deploy telescopes in Australia, in particular, an spectrograph, the ANU 2.3 meter, and then near infrared and optical photometers. So I'm going to show you a little bit of how the portal works, the data transfer works, and the API, like the tutorial. I'm not going to touch the multi-messenger gravitational wave, but I'll show you where it is. So this is a video pre-recorded yesterday on the portal. Basically, you get there, you have API, the tutorials, you have the gravitational waves on top, but now we have a new bar where you can actually get recommendations in real time of what you want, what you're searching for. In this case, I'm searching the latest alert that we just got in our database. Here, we're searching for a TNS classified object, so we have that name resolver. And here we're searching for a class. It can be a candidate class, like a supernova candidate, or it can be something known like TNS reported, Sinbad, cross-match, etc. In this case, it's early type 1a supernova candidate. We're going to see the first 100 events, and you can see the light curves. This has changed in the last months due to community feedback, so it's pretty cool. I really like the table view, which a lot of people don't like, but then you can filter out in the columns and play with it, which for me makes a lot of sense when I'm searching for a type of object. In this case, I'm searching at least 10 measurements. You can go in, get the light curve. You get, of course, the difference with photometry, but you can get things like color, the DR photometry from CTF. And in this case, it takes a while and there was none, but then you can query the alert content and take a look, for example, the supernova classifier scores, the coordinates in different coordinate systems. You can download data directly with buttons or just figure out to do it in your terminal or in a Python. And then you have buttons like TNS, data center, etc. And you can even have a QR code if you want to share your favorite thing. Here for the supernova tab, we have a profile that shows you color evolution, magnitude rate, machine learning classifications. I think here I wanted to show you a variable star to show you also that we can fit a variable star in real time. In this case, I'm taking, I don't remember which one, I'm guessing the middle one. And we're gonna feed it with the variable stars profile that you can see there. Oh, I don't know why I clicked back there. It was a video. Probably it was very slow. My internet was not great at that point. So imagine that I'm doing it in real time and it takes a while, but probably you can access it much faster than I was. But you can feed the variable star light curve, which I don't know what happened, but I am not moving. Because I'm getting all the DR photometry, which is a lot. And you can see that we just got 2,000 points. Now we're going to feed the variable star in a parallelogram, or you can feed a microlensing event, etc. Now that's the Science Portal 101. You can go in and look at the data. It's all public right now. The other thing I wanted to show you is the Fink data transfer. So we have a data transfer system. It's in the top left corner. You can download CTF data, but also the light curves from Elastic, the different versions. In this case, I'm downloading the CTF data from the last week. And I am searching any of the classes that exist. It can be all classes or it can be certain classes. And you can just select a class and then get the data, but you can also do something different. Like, for example, I'm searching for space debris satellite gleams or NPC objects that I want to add, for example, that are quite faint. So you have the documentation here, how to do it. Basically here you can see the syntax of the filtering. Here I'm gonna put a magnitude limit, which is very easy. You just set it there. And then what I'm gonna do is to download a light curve only. I'm not gonna get the cutout. Now, when you do this, we do an estimation of the number of alerts, but that doesn't include the cut that you make, but it's to give you an idea how many should you expect. And here we're sending the job to the cluster. It's updating, it's starting. And as it goes, it's actually quite fast unless you want to do bulk transfers, which is a sad phase because please don't break the system. But basically using this line, using the Fink line, you can download the data in your computer and work with it. So this has been very useful and a lot of people have used it even for the Elastic challenge. And the last thing I wanted to show you is that the Fink tutorials, we have a GitHub page that is linked in our finkportal.org, where you can actually go and see some of the tutorials we have created. In this case, well, there's a lot of them. And in this case, I'm going to show you one on photometry. Basically, these are Python notebooks that you can go in and see how can you query our database in real time and manipulate the data. In this case, understanding the difference between the magnitudes that we present in the portal and are delivered by CTF and eventually Rubin. So basically, it's a way to, you can clone that, you can run it in your computer, it should be completely reproducible. Of course, we love feedback. So if you find a bug, something doesn't work, you want to add a new filter, you want to change something, we're more than open to hear it. For us, it's very important to have your feedback. And I'm going to finish up not with a conclusion, but more like, what do you want to do and what do you want to know? And some questions that I'm happy to answer, or you can ask me any question that you want. Julian is also online, so tough technical questions for him. Thank you very much.
Questions?
In your initial slide, you had like Tom in the slide as well. Is there like, does the Fink talk to Tom very like, are all the functionality already in Tom, or is it very limited right now?
Thanks for that question. I'm guessing you're talking about this slide, that there is a Tom toolkit. So we are using the Tom toolkit as a architecture for doing this system that connects Fink with telescopes. That's something that is going to be deployed soon. However, Fink already has a plugin in Tom toolkit. So you can already fetch the data from our database if you have a deployed Tom toolkit. It's called the Fink plugin, Fink Tom, sorry, or Tom Fink. I never remember which side, but I can send you the link if you're interested.
That would be great. Thank you.
Yes, go ahead. Are you planning on uploading your slides to the meeting agenda?
Yes, sure. I can add that. Well, I'll send it to Melissa. I think I cannot upload things, but I will.
To upload, but also I will do it.
Perfect. You will have them then.
Any final questions? All right, thanks again.
Thank you.
No one from Anais Broker. Okay, thanks. None of the Antares folk were able to be here, so Tom Matheson sent me some slides and I would do my best to speak to them. So Antares is one of the event brokers, one of the alert brokers that's being built at NORLab. It's going to offer public access to Rubin alerts. It does ZTF alerts now. It's deployed on the Google Cloud. Antares also adds value with contextual information and past history. So it's doing things like adding value to the filters that you as a user can then use and search on for your science. It's got similar capabilities as you've heard of already, such as the watch lists. You can set it up to notify you when something appears in the sky that is, in one of those regions of interest that you've defined as a watch list on the sky. And it also offers direct integration with the target observation managers and the AON system. Acronym I forget, but it's the AON system works to automatically schedule follow-up on telescopes that participate in the AON network. So you can do all of that from Tom's Antares. And the website for Antares is there at the bottom for you. A screenshot of so right now, Antares, like many of the other alert brokers, are actively processing ZTF, ZTF stream. It is one of the 7 or so Rubin selected brokers. You just heard David talk about how they are actually getting the alerts for snaps from Antares. And they're also going to be fulfilling Rubinstein for an internal alert filtering service, which is a bit of a detail, but it just means another way for users to get direct access to alerts. You would do it through Antares. Tom Matheson's instrument paper for Antares is available there as a link. So one of the key science capabilities of Antares is being able to filter alerts. Filters are just little bits of Python code that use features and the information that comes from the alert packet to say, yes, this particular object does or does not match my filter. So it's bright enough to match my filter. It has the right light curve shape to match my filter, that kind of thing. So this here, I think, is just a screenshot of some Python that just to demonstrate that filters can be written in Python. And Antares accepts user filters. So you can design one, test one, and have them adopt it. And then you can have the results of that filter streamed to you in real time. As I mentioned, they can be simple, certain just cuts, or more complex, like it does some light curve analysis on an alert and then passes it or doesn't. The Antares operated several classifiers for the challenge. So that is open for you if you want to become an Antares user. Here's some of the back-end technology that I know a lot less about. Very impressive flowchart here. And I'm just going to refer you to this website for more information about that. As a user, I think you don't need to know most of this stuff. It's more for other broker developers. And yeah, so the message here is it's open, it's there, it's ready for you to use on ZTF alerts. So try it for yourself. I have an account. You can make an account and you can set up your watch lists and get going. The Antares team is really open to feedback. They want to know what you might like to do with Antares. So I could try to answer a few questions, but probably I'll just pass them back to Tom. He'll be back in email contact, I think, next week. So yeah, that's it. I'll take questions if I can. Okay, you've got the links, so you can go check it out. Just waiting to, I guess I should check this back. Oh, thank you, Sarah. Astronomical Event Observatory Network is what it stands for. Oh, I got them this year. Nice questions, so if you ask them in Slack. Otherwise, we're going to move on to the last talk of this session. It's on the broker called Ample. And Jacob should be here. Clint, can you unmute?
Questions, can you hear me?
Yes, we can hear you.
Okay, let's see if I can share. And can you see something?
Yes, thank you.
Okay, excellent. Hi, everyone. I'm Jacob Nordin, calling in from Berlin to discuss the Ample platform. So I'm very happy for the opportunity. And I think, as all of us, I'm very excited to actually get alerts pretty soon now. So what's Ample? It's a slightly different beast from all of the very excellent brokers we've heard about so far. There are a number of words there. Let's see if I can switch slides. Yes. I think the easiest way to understand what it is with normal kind of words is that it enables code to data, which is a pretty common acronym now. The idea is that what we have to do is to develop code software locally where we're used to use it, but actually not do computations there. We upload it to where the data lives to scale operations. Some of the reasons are obvious. With LSST, we will have alert rates and data rates that we can't handle individually. That's the motivation for brokers in the first place. It's also going to be essential to develop continuous good software. And now in astronomy and astrophysics, projects are so complex that we can't write any more projects that are developed by a student or a postdoc and then discarded. We have to think about long development cycles and modern software development tools. Another reason is that we want to have fair and reproducible analysis, and that's hard in time domain work. So we want to be sure that what we do can actually be traced and reproduced. And we also want to have ways to change domain knowledge. It's another consequence of a complex field. Some will be good at training AI models, others at understand actuation processes, and so on. So we need ways to interface there. And modular code-to-data frameworks is a way to achieve those goals. So I'm going to spend most of the time talking about a really stupid dummy science example. So this is again going to touch about multi-measure studies and thinking about the idea that maybe the reason we're not seeing kilonova is that they're actually associated with a 42-day linearly rising optical light curve. Could be true, so let's find out. And the first part of this study is something we can, all of us do, write a simple Python module that evaluates some sort of light curve, checks whether it has the shapes we want to have, and then returns some sort of quality of fit. Now, the hard part of this is usually, so how do I take all of this and in a consistent way expose it to this kind of torrent of data? And that's kind of what you need some sort of modular framework to do. And that's kind of what illustrated in this little figure to the right. You have little boxes. Those are different modules that do different things. For example, the top one grabs alerts corresponding to some heel picks region. Then we have another box that filters them. Then we have a third box that does this linear fit. So that was the function we saw. And then we might have some reactions that could be either you set an alert right away or you note your telescope or you just print a table. And the idea with a processing framework is that you can have most of these modules available off the shelf. You pick them out of existing software libraries, and then you add the component that you found or that you thought out. And in this case, it would be the T2 line fit. So all of this exists as a configuration file that basically lists what units they want to do. I'm not going to bore you with the configuration file. You have the full trace here in the uploaded slides that you can have a look at. The key thing is that once you have this file, then this is something that you can distribute and share. So anyone can take this, install the AMPL libraries, and run it locally on their machine. And this can be then something you distribute with your publication. It can be something you share with your friends for continued development. Can be to trace what you've been doing. If you would run the workflow that I pointed, you will match a LIGO Virgo alert with linearly rising sources, and you will find things like this little thing that you that you see to the right. And you might ask, should you be excited? Probably not. And then as with an analysis, you would then be faced with kind of the next order of questions. So what does this actually mean? And this is kind of where you get to the real power of this workflow configuration files. You can continue them. You can update your Python file with a full-grain machine learning model. You can go back and process the full ZTF archive to get maybe some background rates or test statistics. That would be a good thing to do in this case. You can instead run on the simulated elastic LSST alerts to find out what they would have given. And now we're finally getting to the topic of this session. Once you have configured your workflow, you can change the input module to use the real-time Vera Rubin alert stream. In that case, you need to upload it to a live AMPL instance where the actual alerts are being run, but it will be the same workflow configuration as you worked with locally. And in either case, the workflow can be distributed, referenced, and reproduced. This is just an overview. So it's a different kind of process. There is no unified front end where you go and look. Rather, you develop an analysis locally, you test it, and once you're satisfied that it works, you run it at scale at the computer center. We will have general machine learning classifiers running on the LSST alert stream. You can see results from the Elastic Data Challenge to the right, and they actually work extremely well, I have to say. Responses within a few minutes and classification metrics above 80% or so. So if this is what you want to have, you can simply choose to have a subset of all alerts that fulfill whatever requirements you want to have delivered to whatever front end you might specify, or maybe just a Slack channel. So this is the mode where you actually use Ample as a traditional broker. This is just sample usage instruction, how to install it locally. I'm not actually going to talk about it, but this way you can install and do some machine learning classification of these elastic alerts. So instead, I'm going to go to my summary. As Ample, it's a platform that runs other pieces of code. It introduces code to data into time domain astronomical analysis. It can be used as a broker based on these general Ample classifiers. But maybe the real reason to use Ample is if you want to do any of the things that we listed here. If you have your own complex analysis ID that you want to try out, if you want to obtain test statistics or background rates, so that you have to process and reprocess archive data or simulations, if you want to design automatic reaction, if you want to make sure that your analysis can be reproduced, or that you have can keep track of what happened, or if you're a machine learning tool developer and actually have developed a pretty cool algorithm that you just want other people to be able to use and reference your work, then you can do that as well. And this is completely public code. You can do this, you can share your classifiers or workflow without involving us at all. So actually only if you want to run it with the full LST alert stream, where you have to contact us to actually upload it to the live instance. So there's a link there to an introductory web page. But if you have more questions, the best way is simply to find me and contact me and start up a discussion. Thank you.
Yeah, go ahead, Mariam.
Okay. Hi, everybody. This is Mariam Majas. I'm faculty at UVA. I would have loved to join, but CrowdStrike thought differently. So I have a question for all the brokers, actually. And I tried to find Gotham, but I'm not sure if he's still online. So one thing that was stressed is that we can, as users, so my interest is specifically in stripped envelope supernovae, the non-1As, and exotic transients, that we can have our own filter, which is great. On the other hand, it's a lot of work. You need a lot of background to make a very solid, ML filter. And so, of course, Elastic, which a number of you have discussed or mentioned at least, was supposed to do that, right, as a community challenge. And so my question is, and perhaps I missed it in some of your talks, and yes, Ample has it very nicely. So are there plans by the various brokers besides Ample to then include the best performing algorithm? Because, with Plastic, which is the prior one, there was kind of a winner, but of course it depended on the training set, which is one of the main things that in the ML session yesterday that Fed Bianco led was like one of the main concerns is like how's going to be the training thing looking like. But I'm curious to hear that. Will there be kind of ways where, Ample, ALeRCE, Antares will say, look, according to this algorithm that was trained on Elastic, this is going to be this object probably. And of course, Anais, I saw on your slide, upcoming things. I saw the subtypes of the non-1As. I was very excited, like type 2Bs. But of course, the paper that you mentioned, the Sanchez says paper, was based on 2021 data, right? And so that did not include Elastic. So I'd love to hear that. And I assume perhaps others are interested in that too, to hear how. And of course, perhaps hot wiring, there was some discussion about that, but I couldn't join that conference. Long question. Thanks for your patience.
And I see your hand is up. Go ahead.
I can answer from the Fink side. I cannot answer from the other broker sides. So our philosophy till now has been, we keep as many classifiers as we can, train with different data sets, and you can get those scores. So you can then select the one that you want. So for example, for finding early type 1A supernova, we have found that we need 2 different types of classifiers to agree to have a very high purity. This is completely empirical. And we know this because we work with the teams that have been training this. So in each classifier, we have different models for these classifiers, and they will all be public. Now, the second part of the question on subtypes of supernova, not only type 1As. This is something that has been very community driven. So per instability supernova, we have people wanting a general core collapse supernova classifier, but it depends on the community that wants a very particular one that we can actually train the algorithms for that and work together towards something that works for the science case. I am not an expert in calcium rich supernova or transients. It doesn't make any sense for me to spearhead that, but that doesn't mean that you need to be alone in that journey. We are open to talk to people and see what we can do.
I mean, if I can, from as I mentioned, these classifiers will be available, and you can just choose a sub thread based on properties of those. But what I would highlight, basically even more than the machine learning classifiers, there will be an ensemble of different classifiers that you can try and that you can use, and maybe they can be improved. Maybe they're basically as good as they will be. And of course, the performance on real data will be worse. I think the real challenge for the science group is to already now figure out, so what do we actually do with these metrics? Based on these numbers, together with the brightness and the number of detections, when should we go ahead and trigger follow-up, for example? What are the subset that we're interested in? What's too confusing? I mean, there's so much that basically science specification that should be done based on those numbers. And there I'm a little bit surprised that work hasn't got very far. There's a lot of discussion about these classifiers, but not really how we put these numbers into use. So that's something where I would really appreciate more discussions with science groups.
And Francisco.
Yeah, so regarding ALeRCE, I mean, I think there are 2 approaches for brokers. One is the filters, and the other is like previous, like curated classifiers. And I think we're more on the second branch. We have curated generalist classifiers. And this is very difficult. It's not just using a simulated data set. You need to test with real data, with the unlabeled data. You can see this in the Sanchez size paper. And I mean, Anais has also done some work with Supernova. It's very difficult. So perhaps we can put filters on top of these generalist classifiers. And this is what people are doing themselves. So they download the generalist classifier and then they do the science. But I think it's very difficult to do this in a filter without having access to all the data from inside let's say, inside the project. And we will provide many classifiers, but we will tell you which ones are the ones we trust more.
That's great. Mariam, thank you for that question. We can continue discussing this in the Slack if need be. As a final note, I just want to say, if this was interesting to you and maybe you want to get a little more hands-on with some of the brokers, starts testing them out, that would be a great unconference topic. So if you're interested in sort of getting together, maybe working through some broker tutorials, somebody get that on the unconference board. I would vote for it. I think that would be a good use of unconference time. Let's give our speakers another round of applause.